Okay, everybody, and good evening. I would like to welcome you to another session of organic chemistry. I hope you all enjoy your long weekend. Did you? Are you all glad to be back here? Of course. Okay, very good. Before we start, of course, I do have a couple of announcements to make. Tomorrow, that is Wednesday, September 5, we are going to have another online review session. And for that session, we are going to use the OWL end of chapter questions in chapter 2 for the session tomorrow. And that session will be at 8 p.m. I will send you a link for those of you who may not have the link, but I will send everybody the link to that session tomorrow as a reminder. Also, I have your quizzes back, so stop me about 5 minutes to the end of today's class session so I will give back your quizzes to you. And I also want to let you know that the homework assignment for this week has been assigned in Blackboard or in OWL. And the due date is Sunday, September 9, 11 p.m. That is the end of chapter questions for chapter 2 in OWL. Okay. So for today, we are going to finish up on chapter 2. Ryan, can you read for us what chapter 2 covers? Yes.
Okay, polar covalent bonds, electronegativity, dipole moment, formal charges, resonance, base acid, and base reaction.
Very good. So these are all of the topics that will be covered in chapter 2. Of course, when we started on last Thursday, we did cover the covalent bond. And we also talked about electronegativity. And before we left, also we discussed dipole moment. So today we are going to start to finish up the rest of the chapter. Bless you. Okay, just to finish up on dipole moment, what you have here is a table from your textbook which lists the series of compounds with the different dipole moments. As you can see here, most organic molecules have a dipole moment less than 3, range from about 3 to, of course, about 1. And those other organic molecules that are symmetrical, we notice here, carbon dioxide has no dipole moment, it is 0, methane 0, ethane 0, benzene also 0. So for the most part, if you have an organic molecule that is symmetrical, the chances are that molecule will not have a dipole moment. Also, if you take a look at this table here, we see sodium chloride has a dipole moment of 9. Now, that is an indication that this is an ionic molecule, because the dipole moment is simply telling us there is a lot of charge separation. In other words, the center of negative charge and positive charge are so far apart, and as such, it has a very large dipole moment. So whenever you see a molecule, organic, any molecule, either organic or inorganic, with such a large dipole moment, you know that the bonding is ionic. In this particular instance, of course, we have sodium being positively charged, and of course, chlorine is negatively charged. Now, I bring this up because this now leads us to another concept that is very important to us. Keep in mind that most of what we have been doing in chapters 1 and 2 are simply designed to lay the foundation for your future understanding of organic chemistry. So we are going to continue in that trend. Now, if you take a look at this molecule here, sodium chloride, we have a charge of +1 on sodium and a charge of -1 on the chlorine atom. So we refer to these charges as formal charges. So that therefore takes us to the next topic that is of interest to us, and that is formal charge. Now, if you take a look at this molecule here, take a look at this molecule here. This is a stable molecule. It is a stable molecule. Now, what we have on nitrogen here, we have a charge of +1 on nitrogen and a charge of -1 on oxygen. So I'm going to go to a blank page to simply expand on this concept of formal charge. So we have this molecule here. Of course, what we are discussing is formal charge. We have a charge of +1 on nitrogen and a charge of -1 on oxygen. Now, if you take a very close look at this molecule here, it is a stable molecule. What is wrong with this molecule? Based on some of the concepts that we have been discussing relative to octet rule and valence rule, what is wrong with this molecule? Do you see anything wrong with this molecule? The what? The nitrogen has too many valence, too many bonds, right? The valence of nitrogen normally is supposed to be what? 3. Very good. And what is the valence of oxygen supposed to be? 2. Okay, so you have here the valence of oxygen according to this molecule here is 1, and for nitrogen is 4. Now, it is therefore, what you see here, it is therefore possible in certain molecules for the atoms within that molecule not to satisfy their valence, or sometimes to have a valence which is more than what is required of that atom. And also, it is also possible for atoms within that given molecule not to obey the octet rule. Now, if you have any one of those conditions, then you must place what we call a formal charge on the appropriate atom. In this case, if you take a look at nitrogen, does nitrogen obey the octet rule? Yes, it does obey the octet rule. But it does not obey the valence rule. It's violating the valence rule. It has a valence of 4, according to here. So therefore, we must place a charge on nitrogen. About oxygen, does oxygen obey the octet rule? Yes, it does obey the octet rule. But does it obey the valence rule? No. Okay, so in this case, oxygen does not obey the valence rule. So in cases like this, you must place a formal charge on the appropriate atom. So let us therefore define what do we mean by formal charge. Formal charge is the charge either positive or negative placed on an atom in a given molecule if the valence electrons belonging to the atom in that molecule is greater or less than the valence electrons of the atom in its natural state. Of the atom in its natural state. Now, what do I mean by natural state? Supposing I ask you, how many valence electrons does oxygen have in its natural state? I mean, 6, right? Okay. How many valence electrons does nitrogen have in its natural state? 5. About carbon? 4, exactly. So therefore, if you have a situation like this, in which we now have a given atom in a given molecule, the valence electron that actually belong to it in that molecule is greater or less than the valence electron in its natural state, then you must place a charge on that atom. Now, how do you do that? So let us assume that we have an acronym for formal charge. Let us use that acronym. So we are going to define formal charge as Fc equals to valence electrons of atom in its natural state Okay, everybody got this? Okay. Yes.
You said the formal charge is the charge positive and negative effect of an atom in a given.
The formal charge is what? Oh no, I'm not finished yet. Okay, well, let me just go to a new page. So we are going to define formal charge as valence electrons of atom in its natural state minus. Notice that this is different from what your book says now. So that is why I'm writing this down. Minus number of valence electrons that actually belong to the atom in the given molecule. Okay? So therefore, let us go back to this molecule here. We have okay, so supposing we write this molecule and then we tell you to place formal charges where they are, where the atoms need a formal charge. Okay, so how, based on the definition that I've just given you here, based on the definition here, what are you going to do? Okay, we start with nitrogen. Okay, what is the valence electron for nitrogen in its natural state? 5. So that becomes 5 minus how many electrons, valence electrons, actually belong to nitrogen in this molecule? 4, exactly. Keep in mind that each one of these now is a bond in which the two atoms are sharing 2 electrons. So only one of those electrons belong to nitrogen. So therefore you have 1, 2, 3, 4. Only 4 electrons actually belong to nitrogen here, and that is what this is saying. This equation is saying, and therefore, so that becomes +1, and that is how you place a formal charge of +1 on nitrogen. Now we do the same thing for oxygen. We do the same thing for oxygen. If you look at oxygen here, what is the valence electron of oxygen in its natural state? 6. Okay, how many valence electrons actually belong to oxygen in this molecule? 7. Okay, that is 1, 2, 3, 4, 5, 6, and 7. Okay, so therefore we place a formal charge of -1. You don't need to say -1. Simply just place negative. If it is, if the magnitude is more than 1, then you got to indicate the magnitude. I'll meet you just a minute. I'll do that with you. Okay. So it is very important to be able to determine the formal charges of a given molecule whenever. If you take a look at that molecule and you notice that that molecule does not obey the valence rule, or sometimes does not obey the octet rule, you must place a formal charge on the appropriate atoms. Your book does this differently. That is why I want to spend some time to do this. It's really very simple. You don't need to really sweat this. Just if you go by the definition that I've given you here, you will not have any problem. Michael, go ahead. How do you know? Say that again. Well, that's a different question. We're going to get to that. Well, the question that Michael is asking is, how do we know that this oxygen here will be the one that will be negatively charged, right? As opposed to whether it is this one here. Okay. The reason why at this point we know that this oxygen is negatively charged is because of the number of non-bonding electrons surrounding the oxygen. But that's a very good question, though, because that leads us to another concept, which we are going to get to very shortly. Now, so let us now take a look at a few other examples of formal charges. Formal charge is very simple. Okay, it is a very simple concept. So, for example, go back to sorry about that. Okay, so we just dealt with the case of nitromethane, which is what I've just given you in terms of determining the formal charge. Supposing I give you this molecule here. Okay. Can you complete this structure for us? What would be the complete structure for this molecule? Is this structure the way it is written, is it complete? No. What is wrong? Okay, oxygen does not obey the valence rule, right? So we need to place a formal charge on oxygen, even though it does obey the octet rule. In this case, carbon does not obey the what? Octet, and also does not obey the valence. So it is violating both of them. So you need to place a formal charge. Yes.
Why can't you assume that the hydrogen is there?
Which hydrogen?
On the carbon in the middle. Like, why can't you just assume?
Okay, now, keep in mind, this is the molecule. If we give you this molecule here, that this is the basic structure for this molecule. That is assuming there is no other hydrogen in this molecule. The way the question would be to complete this structure, okay? And that is what you have in there is what you have. There is no other atoms here.
Okay.
So in this case, what would be the formal charge on oxygen? Very simple, right? 6 minus 7 minus 1. Okay, formal charge on carbon plus 1. So we don't really need to spend too much time on this. Yes. 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 Okay. Now it is important, even though it is a very simple concept, but as we move on, this is going to become very important. Because many of the chemical reactions that we are going to be dealing with, a lot of the intermediates do actually involve molecules that need formal charges. You have to place those formal charges on those molecules. Okay, so now this takes us to another concept, which we call resonance. Let's see here. Another concept that we refer to as resonance. We are going to spend some time on this particular topic. Now, supposing I give you this molecule here. Supposing I give you this molecule. Keep in mind we have hydrogen here. We have hydrogen here. Right? And then I say I move this pair of electrons. Remember that the pi electron, this pi electron here, you have two p orbitals. You have two p orbitals between this carbon and this carbon sharing one electron. Supposing those two electrons decide to go to only one of the p orbitals. And then what do we get? We get this molecule here. In which now we have moved the pair of electrons. Notice anytime we draw an arrow, we draw an arrow, that arrow is simply indicating the movement of electrons, indicating in this case the movement of two electrons. If we draw this type of arrow, one-sided arrow, that is movement of one electron. If you draw two-sided arrow like this, that is two electrons. Okay, so as we move on, this is also will be one of those things that we are going to be using. Okay, so in this particular instance, what do we have? We have here, we move this pair of electrons to here. So now this molecule here, this carbon now, has a formal charge of -1. And therefore this carbon here has a formal charge of what? +1. Okay? These two structures here, we refer to this as resonance structures. notice what have we done here. All we've done is, to indicate resonance structures is simply move the pi electron from one atom to be under the control of only the other atom. In this case, you have a positive charge, you have a negative charge. So these two molecules, therefore, we call these resonance structures. And so therefore, this molecule here, which we call cyclohexene, we say this molecule is an hybrid of two resonance structures. Now, what do we mean by hybrid? It simply means that if we take a look at this molecule here, it is behaving as though it is this structure A or structure B. So resonance in essence are different structures that are used to represent the same molecule, in which the difference between those structures is the positioning of the pi electron or the non-bonding electron. Let me write that for you. Yes.
Okay, you said that the first method to draw from truth is the hybrid of two of the we can draw the method, correct?
No. These two structures here. This and this are resonance structures. So therefore, we say this molecule here, cyclohexene, is an hybrid of two resonance structures. It's an hybrid of this structure and this structure. In other words, what we are saying here, this the molecule that we call cyclohexene behaves as though it is this structure or it is this structure. It's almost like when we say you are an hybrid of your parent. Okay? Sometimes I see you, I will see your dad. Sometimes I see you, I see your mom. It isn't to say that you are either your mom or your dad. It's just simply to say that you are an hybrid of both of them. So what we are saying here, we really do not know the exact structure of cyclohexene. But cyclohexene behaves as though it is this molecule here, or it is this molecule. That's what we're saying. And you're going to find this all through organic chemistry. And we use resonance to explain a lot of the processes or the phenomenon that you're going to find in organic chemistry. Okay, so this is very important indeed. So now let us give you another example. Still on resonance. Supposing I have this, I give you this here, and I tell you to give me a resonance structure, another resonance structure of this molecule. What will it look like? By the way, the symbol for resonance is this here, this two-sided arrow. That is how you represent resonance. Supposing I ask you to give me another resonance structure for this molecule. This molecule is called acetone. What will it look like? What do you have to do? Keep in mind, in resonance, all you move is you either move the pi electron or you move the non-bonding electron. You cannot do anything else. Okay? If you do anything else, then that is no longer resonance. Resonance is just the different separate structures representing the same molecule, in which the difference between them is the positioning of pi electrons or sigma, or non-bonding electrons. Yes. Somebody asked it. Yes. Oh, I thought you were raising your hand. Okay. Okay, so what would this be? The resonance structure would be what? You simply move this pi electron, right? Okay, you don't have to draw the arrow, but I will just draw the arrow. So you simply move this pi electron to here, and therefore you have and when you do that, we then have to show formal charges. Okay, so what will be the formal charges now? -1 on oxygen, right? Okay. And positive, exactly, very good. You see how easy this is. So Let me simply give you a definition of resonance again. Different structures are representing the same molecule in which the difference did I get that right? Difference between the structures is the position let me continue here. Position of the pi electrons or non-bonding Okay, yes, somebody has a question there. To do what? Move the pi bond to the... Oh, okay, very good. Excellent question. Okay, the question is, why don't we move the pi electron? In this case, why don't we move the pi electron to this carbon, right? Okay, very good. Excellent question. Okay, just I'll be right with you. Okay, so, go back. It was? Oh, right here? You got it? Okay. Okay, the question that you asked, let us address that question because it is very important. The molecule we have is this here. Very, very good question. Remember, when we did hybridization and bonding and stuff, this carbon is what kind of hybridization? sp3 carbon. This carbon is what? sp carbon. This oxygen is what? sp oxygen. Resonance only involves sp or sp2 atoms. Keep that in mind. That is most important. That is why I say that's a very important question. Resonance, I will write it for you. Resonance only involves sp or sp2 atoms. And never will resonance involve sp3 atoms. Because for resonance, you only need to move either the pi electron or the non-bonding electron. For you to involve an sp carbon, that means you have to break a sigma bond. You can't do that. Okay? For you to involve an sp3 carbon or atom, that means you have to break a sigma bond. You cannot do that. Okay, so that is very important. Okay, so that is the answer to your question. And that is why on this carbon here does not have a p orbital available to it. So we cannot move electron to this carbon. Neither can we move electron to this carbon, because those are sp3 carbon atoms. So the only atoms that will be involved in resonance will be the carbon, this carbon here, and this oxygen. Okay? That is very important. Okay. So therefore, supposing I have this molecule here. Supposing I draw that molecule for you. I want you to give me at least 4 resonance structures from this molecule. 4 resonance structures. 4. No, this is not benzene. Keep in mind, what do we do with resonance? We move pi electrons. Okay? Okay? So give me 4 resonance structures. Okay, so you want to move what?
The first position to the second position.
Okay, very good. Let's number this position here. 1, 2, 3, 4, 5, and 6. Okay? Okay, so you want us to move this pi electron to those 2 electrons to under the influence of carbon number 2, right? Okay, very good. We could do that. Supposing we move that to here, keep in mind we use the arrow to show the movement of 2 electrons, the regular arrow. So what will be the resonance structure once you do that? What will it look like? What will it, this double bond you see here, that we didn't change that, right? Okay, so what will change is this pi electron here. So this becomes, what will be the charge on this carbon here? Carbon number 1? +1, because you move this electron away to here. So this becomes +1, and this becomes -1. Okay? Now, that is one resonance structure. Can you draw another resonance structure? Yes, that's what we're doing. That's what you do. Just move. Okay. Okay, like, okay. From between position what and what?
Okay, so if you do that, the one at position 4.
Okay. Carbon number 5 is an sp3 carbon. Keep in mind, that's what we told you. Do you see that? Carbon, whatever resonance you draw cannot involve carbon number 5 or 6. Is that clear? Because those are sp3 carbon. Those very, very important. Okay, so therefore, given that in mind, so what do we do? We could move. Make another carbon sp? No, you cannot change the hybridization. You cannot change the hybridization. Okay, why don't we move the pi electron to carbon number 1? Can't we do that? Huh? Oh, I'm sorry. I see. Okay. Okay. Now, why don't we move the pi electron to carbon number 1? Can we do that? Would that be a resonance structure? Would that be an acceptable resonance structure? Why not? Why not? All we're doing is moving a pi electron between the sp and the sp2 hybridized orbitals. Okay, so if we draw another resonance, keep in mind this is the symbol for resonance. And then I will draw this. This time, what am I doing? Let me take this off. This time, what do I want to do? I now want to move this here, pi electron to here. Okay, and so I get negatively charged carbon, and this carbon become positively charged. Okay, so right now, let us begin to now label these molecules here. Let us call this molecule A, B, and C. This here. Those three molecules, A, B, and C, those are resonance structures of the same molecule. So can we draw additional resonance structures? Which one? Between what? 3 and 4. Okay, very good. So let me take this out. So the concept of resonance is very simple. Simply moving pi electrons. That's all you do. We spend some time on this because for the most part, the rest of the organic chemistry mostly deals with explaining different reaction phenomenon using resonance. So that it is important that you understand the concept, even though it is a very simple concept. Okay, so now we could also draw another resonance structure in which we simply say, okay, all we want to do now is move the pi electron between carbon 3 and 4, right? We should show the arrow, we move the electron to carbon 4. And then what do we get? This here is still here. We did not change that. Now we have the electrons are here, negatively charged, a formal charge of +1 on this carbon here. This here, let us now call this ABC structure D. Okay, so those structures A, B, C, and D, those are resonance structures of the same molecule. And all we've done is simply move electrons around. Okay, can you draw another resonance structure? Between what? Where would the electron go? Electron could go from could go to carbon number 3, right? You could do that too, right? Okay, so we could have in this case, we say all we want to do now is move the pi electron that is between carbon 3 and 4. We move it, those two electrons, under the control of carbon number 3. Hey, just a minute. Okay, so now what do we have? We now have, keep in mind this one is still here, we didn't change it. Now we have 2 electrons here. That carbon is negatively charged, and this carbon is positively charged. Now let us call that A, B, C, D, E. Okay, so all of those structures are representing the same molecule. We call them resonance structures. In other words, the molecule, this molecule here, is an hybrid. Whatever this compound is an hybrid of all of these structures. In other words, when it comes to chemical reactions, this molecule will be reacting sometimes as though it is any one of these resonance structures. Yes, somebody has a question there. Yes.
Okay, so you can't move the double bond to the electron of the like to a lone pair of the carbon. Like I couldn't do like 4 and 1, right? You know?
Can you do 4 to 1?
Like if I wanted to move the electron pair from 4 and 3 to like 1.
Okay. If you want to.
Right, because it's not connected to the bond.
Okay, very good. It is. There is a way you could do that. Okay, let us look at what we've done here. In other words, can you just move the pi electron, not just between the 2 adjacent atoms? Okay, very good, very good. There is a way we can do that. Okay, now let us look at this here. Look at all of these resonance structures I've drawn, right? Let us take a look at resonance structure number B, right? Supposing, can we draw another resonance structure? Can we draw a resonance structure? Yes, we can. You could draw resonance structures as long as you have atoms are connected to each other in which they are all sp2 or sp atoms. In this case, we could draw a resonance structure here in which we take this pi electron here. Okay, we could move this pi electron to, because in this case, what this is saying here, this carbon here, as an empty p orbital. That is what that positive charge is telling you. Keep in mind when we were dealing with hybridization, you have the p orbital. So what this positive charge is telling us, there's an empty p orbital here. So you could move the electron into there. Therefore, we could do this. So that this pi electron now will now form another pi electron between this carbon here and this carbon here. And what would that resonance structure look like? What would it look like? It would look like this. Now the double bond will be here, right? And the negative charge is still here. Now where would the positive charge be now? Carbon number 4 right here. Okay? That's a very good question you did ask, because what we've done here is what we call electron delocalization, because resonance allows us to do what we call electron delocalization. And you will find, as we go along in organic chemistry, the more resonance structures you can draw for a molecule, the more stable that molecule will be, because the resonance allows you to delocalize the electrons along the carbon chain. Okay, and that is essentially what we've done here. Okay, so here, what we have, this is another resonance structure. Let us call this ABCDEF. You can see as many resonance structures as possible here. Yes?
How do you know that a pair will charge as opposed to just
How do I know that a pair of electrons can move?
yeah, as opposed to just one electron?
No, okay, yes. Well, that's the whole idea, that in nature, those two electrons, I mean, it is possible that one electron will move, but that is not what generally we observe. What happens, those two electrons move. Okay, those two electrons will move to one orbital, to one carbon atom having that orbital, and then leaving the other orbital completely empty. Yes, it is possible only one electron will move. In certain instances, you may have that. That will also be a resonance structure, but generally that is not as stable as when you have both of the electrons moving. Okay. Now, I also do want to make something very clear. Resonance is not an equilibrium between two structures. In other words, just like we have, you cannot show resonance by doing this. In other words, that's by saying that these two structures and this structure B and F, they are in equilibrium with each other. No, that is not resonance. Okay? Resonance is not a case in which you have two structures are in equilibrium. No, that is not the case. Resonance simply means that each one of those structures could represent that given molecule at any given time. Okay, now also, yes. Which one? Can you raise your voice so I can hear it? Okay, just a minute. Can I move let me go to, so what you are saying is, can I do this? Okay. So we have carbon 4 right here. So you want me to move these electrons here to where? To carbon 1. Okay, when you do that, you got to move them through the nuclei. You have to move them through this chain of carbon. Okay, in other words, you have carbon 1, carbon 2, carbon 3, carbon 4. Whenever you do that motion, moving those electrons, you got to move them through the p orbitals of these 4 carbons here. Okay, so those 4 carbons is what we refer to as being conjugated. In other words, you have anytime you have a series of atoms that are either sp2 or sp3 and they are joined together, that is what you say that those atoms are conjugated. And as such, you could move electrons along the p orbitals of those atoms. That is the way you do that. You cannot simply just move this to jump from here directly to here. You cannot do that. It has to be along the carbon skeleton. Okay. Okay. So therefore, you can see the whole concept of the whole idea of resonance is a very important concept in our organic chemistry, and it is something that we are going to continue. We are going to revisit and come back to this whole concept as we go along during the course of this semester. Another thing I would like to also let you know, if I have this, I said these 2 structures are resonance structures. I said they are resonance structure because what have I done? All I've done is simply move this pi electron from between carbon and oxygen, move it to oxygen. That's all I've done. So these 2 structures are resonance structures. However, because they are resonance structures does not mean they have the same energy. In nature, you find that this here, of the 2 resonance structures, this is the most stable. And how do you know that? Anytime you have resonance structures, the resonance structure that is neutral, that has no negative or positive charge, is more stable than the one that has charges. Keep that in mind. The resonance structure that has no charges is more stable than the one that has charges. In other words, this molecule here, even though it is a resonance structure of this, it is more stable than this is more stable than this here. So we say this is less stable. So the more charges you have on a resonance structure, the less stable that resonance structure is. Yes.
For the previous example,
yes.
when we had A, B, C, D, E, whatever.
Yes. Okay.
How many resonance structures would you say you have? Would you just count the ones that you changed, or do you count all of them?
You count all of them. All of them. So all of these here are resonance structures of each other. They are resonance structures of each other. So you can see the whole idea of formal charge leads to resonance structures. Okay? Because once you draw resonance structures, you must indicate the formal charges. Okay. Now, supposing, yes.
Are these all the resonance structures you can draw?
Well, you could draw as many, you could draw some more, I could draw some more.
No. How do you know how many?
Well, as long as all you do is move pi electrons.
So would you ever ask me to draw all of them?
Well, I would be reasonable enough to say, give me 5 or 6 or 20 or whatever. I will give you something. I will give you some number. I'm not just going to let you dangling out there. So no, I will give you some numbers. Okay. Okay. Now, supposing we have this. What time do we have? Okay. Plenty of time. Suppose you have this. How many resonance structures of this molecule can you draw? How many resonance structures can you draw? How many? How many? Take a guess. How many? 4. How many people say 4? 6? Okay, let's have that. Let's have that. let's draw the neutral. Let's draw the neutral resonance structures for those that do not have any charge. Okay, give me one that doesn't have a charge. Okay, what will it be like? Yes, make it. Move all of the pi bonds, right? If I move this pi bond to here, right? In other words, now I want to increase the complexity of what we've been discussing now. Supposing I simply move this pi electron to here, and when I do that, I could also move this pi electron to here, and when I do that, I could move this pi electron to here, and what do I now have? Now, where would the double bond be? Double bond would be where? Right here, right? Right here, where you had the single bond before. Okay, these two, let's call this A, let's call this B. A and B are resonance structures of each other. Resonance structures of each other. Okay, those will be the most stable of the resonance structures. Can you give me some other resonance structures of this model? Can you give me some other resonance structures? Want me to label the carbon for you? Okay, let's say carbon 1, 2, 3, 4, 5, and 6. Okay, let us move the pi electrons now instead of moving all of them. Yes. Okay, move 1 to carbon 2. Okay, move to carbon 2. Okay, so that will give us this here. In other words, move the pi electron between carbon 1 and 2 and move those electrons to carbon 2, right? Okay, so now you're going to have electron here, and that is negatively charged, and this carbon therefore will be positively charged. And what happens to the rest? This still here. We didn't do nothing to them. Okay? So this is also where is this coming from? Okay. Okay, this is C is also a resonance structure. But which is the least stable of the resonance structures? Which is the least stable? C. C is the least stable. Okay? Can you draw some other resonance structures? Okay, I will leave that to you guys. Okay? Just a question of moving electrons around. Okay? So resonance structure is really very simple, but this is a concept that we are going to revisit during the course of this semester. Okay, so now that leads me to the last topic or concept in this chapter that we need to discuss. Oh, by the way, yes. In drawing resonance, keep in mind, of course, in drawing resonance, it is possible for you to violate the valence rule. but you cannot have more than 8 electrons surrounding a given atom. Okay, the octet rule, you need to be aware of the octet rule. In as much as possible, try to obey the octet rule. But you cannot violate the octet rule by having more than 8 electrons surrounding a given atom. So you cannot make a resonance atom. For example, in this particular instance here, that is what this is trying to tell you, that this is not an acceptable resonance structure. Because all we've done here, we moved the pi electron to this non-bonded electrons between oxygen and carbon to here, and therefore what happens here, you now have this carbon has 10 electrons surrounding it. So it is violating the octet rule by having more than 8 electrons. You could have less, but you cannot have more. Okay, so keep that in mind. Okay, the last topic now, before we finish this chapter, is acid-base reactions. Supposing I have this. This molecule here, this is acetic acid. This is the component of your vinegar. I'm sure many of you eat vinegar in your salad, right? This is what you eat when you do that. This molecule here. It's called acetic acid. If you have acetic acid dissolved in water, let us keep in mind the non-bonded electron on all of this. There is an equilibrium that is established in which the acetic acid will react to donate a proton to water. In this case, the acetic acid will be acting as a Bronsted acid. What is a Bronsted acid? According to general chemistry, any species that donate a proton is a Bronsted acid. Okay, so therefore, you could have the acetic acid will donate this proton here to oxygen, to water, in which now water will now have a formal charge of +1 on oxygen, and a formal charge or oxygen of water, and a formal charge of -1 on one of the oxygen of the conjugate base of acetic acid. Now, so we say this is the acid because it is donating a proton. We call this a base, and so this will be your Bronsted base. And then here, the product that you obtain when you lose that proton is what we call the conjugate. Okay, this here we call this is the acetate ion. So the acetate ion is a conjugate base of the acetic acid. Okay, after you lose the proton, what the product that you obtain we refer to as a conjugate base, and then this water here is picking up a proton from the acetic acid. The water is acting as a base, so therefore the product that we obtain here, which we call the hydronium ion, okay, this hydronium ion we refer to as the conjugate acid of water. Which is the conjugate acid of water. Now, how do we know whether this reaction will go? What direction this reaction will go? Notice what we've done here. We're giving you an equilibrium that the reaction could go both ways. But in reality, actually, the reaction goes more to this side. More of the reaction goes more to the right. How can we say that? How can we predict what direction this reaction will go? The way you do that, we have a set of what we call the acidity constant. In this case, the acidity constant, Ka, for acetic acid, in this case, would be the concentration of the conjugate base, in this case, the conjugate base of acetic acid, and the concentration of the hydronium ion, divided by the concentration of the initial acid itself, and the concentration of the initial base, in the case of acetic acid, this value is about 1.74 times 10 to the minus 5 moles per liter. Okay, that is the acidity value for acetic acid. Now, what we do to therefore find the relative acidity for different molecules, what we do is to convert this acidity value here to another unit we refer to as the pKa, which is the negative log of Ka, so you don't need to remember all that. In the case of acetic acid, the pKa for acetic acid, let's say it's about 5. For water, the pKa for water is about 16. Now, the lower the pKa, the more acidic that compound is. In other words, if I ask you, between acetic acid and water, which is the more acidic? Which is more acidic? Acetic acid is more acidic. You have acetic acid reacting with hydroxide anion. The hydroxide anion picks up the proton from the acetic acid to form the acetate, and then you form water. And therefore, you have the strong acid, which is at a pKa of close to about 5. I told you about 5. And then the weak acid, which has a pKa of about 16. Oh, I see what is wrong with what I gave you earlier. What I gave you, let me go back to that. I think I made a mistake in that one. Oh no. Oh, okay. This was meant to be, I knew there was something wrong with it. This was meant to be hydroxide anion. Okay, that's meant to be hydroxide anion, and then therefore this will be water. Okay, so how do you then determine you have a pKa value here, 5, and then the water has a pKa value of 16. Okay, sorry about that. So the direction of acid-base reaction goes from the direction of strong acid, relatively strong acid, to relatively weaker acid. So in this case, this reaction will go in this direction. So I think we have finished chapter 2, and then, of course, what I want to do now is give you back your quizzes. Now, do not forget tomorrow, we have the online session tomorrow, and those of you who, for whatever reason, have not been able to log into ours, you should see me after I give out the quizzes.
Differentiated force can't transfer the category.
You cannot do that.